Today I'll be sharing with you my tips, tricks, and advice for getting better at solving problems. Now, in my opinion, problem solving is one of the most important skills that you can have, especially as a programmer. And actually, I'm not the only one that agrees with this. The largest tech companies in the world evaluate you almost entirely based on your problem solving ability, and that's why we have the famous coding interviews. So in this video, I'm going to walk you through the entire process of breaking down a problem, solving it right from the beginning until the very end. We're going to start by understanding the problem. We're then going to develop an algorithm to solve it, and then I'm going to code this out live in front of you so you can see exactly how an experienced programmer goes about solving these types of problems. The specific problem we'll look at will be a medium level question from LeetCode. These are the type of problems you'll probably get during a coding interview. It will make a good example so you can understand how to solve something that's not super easy yet not extremely complicated. However, before we get into that, I know that the reason a lot of you are watching this video is because you want to land a software development position. Now, I won't lie to you, in 2024, it's a lot different to land a role than it was even just a few years ago, and it can be really, really competitive. Now, that's actually why I teamed up with HubSpot and wrote an entirely free guide called How to Land a Developer Role in the World of AI. Drawing on my over a decade of experience, this summary covers the best programming languages to master and the most effective ways to learn them. It also goes over best practices for your resume, how to create your portfolio, and recommendations for YouTube channels and other resources to enhance your development skills. You can check it out for free from the link in the description. Personally, my favorite part is the long list of resources, including YouTube channels and websites that showcase fantastic free ways to improve your skills. This content is focused on helping you distinguish yourself as a programmer in this AI era, offering essential insights and strategies to help you remain competitive in the developer industry. I'm thrilled to collaborate with HubSpot on this resource and to have them sponsor this video, enabling me to provide all kinds of free content like this video to you. So let's begin here by going to the computer and having a look at a problem that I've selected. Now, this problem is called Rotate List. It's a medium problem on LeetCode, and again, most of the time you'll be given medium type problems. This one is not extremely difficult, but it's actually a really good fit for this video because it won't take us super long to solve, but you'll get an idea of how we go through the process. So the first thing we want to do if we're in a coding interview situation or really just trying to break down any problem is we want to make sure we have a thorough understanding of what the problem is. In a lot of situations, the problem will be read to you. In that case, feel free to ask for clarification, ask them to repeat themselves, and just make sure you really understand it before we start solving. In this case, I'll kind of read it to you as we go from the prompt on the left-hand side of the screen. So it says, given the head of a linked list, rotate the list to the right by k places. And it shows us a visual example, which is quite helpful. You can see the original list, 1, 2, 3, 4, 5. And if we're rotating by 2, which is the example right here, then you'll see that the rotation ends up with 4, 5, 1, 2, 3. So this is pretty straightforward. We're taking the k elements from the end of the list and then rotating them to the front of the list, or whatever way you want to look at it as. But that's kind of the way that I see it. I see 1, 2, 3, 4, 5. I see the first rotation, 5 goes to the front. And I see in the second rotation, 4 goes before 5, k equals 2. So we've taken those two back elements and kind of just placed them at the front. Going down, we can see we have example number 2. Now this one's a bit more complicated where we have k equals 4, and that's the amount of rotations. In this case, I notice immediately that 4 rotations is more than the length of the list, which is 3. And you can see that when we end up rotating this, we get kind of a different result where we need to rotate multiple times, and we end up eventually hitting the original list. So you can see we have 0, 1, 2, we do 1 rotation, 2 rotation, 3 rotations, which brings us back to the original list, and then we have 2, 0, 1. So we also see that we have some constraints here. We can read through those if we want, but overall a pretty easy problem to understand, but I would want to make sure again that I'm clarifying this with my interviewer. So if I was in the interview situation, I would be asking them, okay, is there a maximum length for the linked list? Could you be sending me a linked list that maybe has no elements inside of it or just has one element? Can k be a negative value, or does it have to be a positive value? I know these might seem like silly questions, but a lot of times interviewers really want to see that you're trying to narrow the problem down as much as possible and really make sure you account for all of the possible edge cases or different considerations. You might assume something. I'd say never assume. Instead, just ask the interviewer. No question is really a bad question, and usually you spend the first few minutes minutes kind of talking back and forth about the problem and just showing them that you do really want to make sure you understand it before you start solving it. So now that we have kind of a somewhat decent understanding of the problem, what I'm going to do is actually go over to the whiteboard. This is what I would always do when I'm solving a problem, and I'm going to start drawing a few things out and kind of visualizing my thought process, one, because it's helpful for me, but two, because it's helpful for anyone else that's watching this, like an interviewer, to understand how I'm actually about to solve the problem. I always find it a lot easier to kind of draw things out, diagram it, even if it's a bit messy, so let's go ahead and do that. So I'm on my iPad now, and I'm going to start walking you through exactly what I would do to solve this problem. Now, I would always start by just writing out some kind of case or example on my whiteboard or on my drawing tablet, just so that I can walk through it slowly and really make sure I understand this, and also just do a few different cases that maybe haven't been given to me. It's always a good idea to take some inputs and just figure out what the output should be. And if you can do this kind of visually by writing it out, then it's going to help you actually devise an algorithm to solve this. So when I look at this, I see that I have 1, 2, 3, 4, 5, I have k equals 3. We know this is very similar to the other input that we were given, and we know this is going to be 3, 4, 5, 1, and 2. Now when I look at this, a few things come to my head. The first thing that I realize is that I kind of have the beginning first 2 elements here, and I have the ending 3 elements here. Now what this tells me is that actually there's kind of 2 ways I can approach this problem. I can take the first 2 elements and I can move them to the back, or I can take the back 3 elements and I can move them to the front. Just because it says rotate right doesn't mean that I actually can't rotate to the left and just do kind of a different approach. Or not really rotate to the left, but it doesn't really dictate the order in which I need to rotate the elements, and it's perfectly valid if I were to take these 2 and put them at the end, because that's going to give me the same result. So just something that's coming into my head, this is what I would be kind of talking about with the interviewer. Even if it doesn't really make sense yet, I'm kind of walking through how I'm going to reach the solution, and this thought process is what people want to see. They want to understand how you're actually solving the problem. Okay, so that's kind of an interesting note that we had, and now that I've done that, and this is pretty easy, I'm going to start looking for a few different edge cases or things that might mess up potential solutions. So for example, I'm going to go with something like k equals 7. Now the first thing I notice when I see k equals 7 is that 7 is greater than the length of my linked list. In this case, I just have 5 elements. Now that kind of intuitively tells me that if I do this many rotations, eventually I'm going to reach a linked list that's the exact same as the starting linked list. So it really doesn't make sense for me to do any rotations that are greater than the length of my linked list, which means I can probably simplify this k value and get a value that gives me the true number of rotations that will reach the end result. For example, k equals 7 is actually the exact same thing as k equals 2. If I do 7 rotations or 2 rotations, I'm actually going to get the exact same result. If I wanted to, I could verify that by walking through all of the rotations, but that's very obvious to me, and I know from the example they gave me that that's going to happen. So this tells me that the first thing I probably want to do is I want to simplify this k value down. So rather than having 7, I need to get the length of this linked list, which in this case is 5. We can see that easily or visually. And I'm just going to take the length, I'm going to take k, and I'm going to perform a modulus. I'm going to say k mod length is equal to the true k, or the real number of rotations that I actually need to perform. In this case, 7 mod 5 is equal to 2, and really the true k value that I'm going to use here is 2. So that's the first part of the algorithm that I figured out, is I'm going to take part of my input and I'm going to simplify it to make my life easier. So at this point, I would start kind of writing down what I know. Even though we haven't solved the problem yet, we know kind of the first step, so let's write that down. Okay, so step 1 is written down, simplify k, and this involves taking k and just modulusing by the length. Now actually, when I write this, I realize that in order for me to do this, I need to know the length of the linked list. And even though I can see it visually when I just write one out, when we're given the linked list in our problem, we're just given the head node. We don't actually know what the length is, so really the first step actually is to figure out what the length of the linked list is so that we can simplify k. So now that means I need to change this a little bit. And rather than step 1 being to simplify k, that's actually going to be step 2. Step 1 will be to find the length of the linked list so we can do the simplification. So now I've written my revised steps. I'm going to start by finding the length. I'm going to simplify the k value, and then intuitively, well, I need to rotate the list. Now, we don't know what's involved in doing that yet, but we do know that will be step 3, and we're starting to work our way towards an algorithm. So you can see how we're kind of breaking the problem down slowly, solving small components of it, and it makes it easier for our brain to kind of handle piece by piece. We look at an observation, we solve a small part, we figure out one step of the algorithm. We don't need to solve the entire thing at once. In fact, it's very difficult to do that. You want to try to do it piece by piece. So now we're at the rotation step. So let's say we have our true k value, right? And we have maybe a simple linked list like 1, 2, 3. For example purposes, let's say our true k value is 2, meaning it could have been something larger, but we simplified it down. Now what we need to do is actually perform the rotation. Now we want to start by kind of assumptions or facts that we know. Now with the linked list, we know that this is singular. What that means is that when I'm on some node here, I don't have access to the parent node, I only have access to the next node. So I need to be careful in terms of how I'm storing these nodes, and actually if I'm doing a rotation where I'm moving an element from the back to the front or from the front to the back, what that is going to involve is me knowing both the tail and the head node. So I know right away when I start solving this that I need to have a reference to the head, which is right here, and to the tail, which is right here. I also know that as I perform these rotations, the head and the tail node is going to change because as I move elements to the front or to the back, well, we're going to have a new head and intuitively a new tail. So we probably want to create some variables where we're storing the head and we're storing the tail. So let me just kind of write some variables here. I don't know if this is going to work, but I'm going to start walking through this and see if I can come to a solution. So I'm going to say head is equal to 1, and I'm going to say tail is equal to node 3. Okay, so I'm just kind of marking them down here so that we have them tracked. Now let's say I just want to rotate one element. That's probably what we want to start by doing. Rather than rotating 2, let's figure out how we just rotate a single element, and then we could just repeat that process as many times as we need to. So if I want to rotate 3 to the front, again, we need a reference to the head, and we need a reference to the tail. So how do I do this? Well, I need to take 3, I need to move this to the front, and to do that, the first thing I can do is I can set the next pointer on 3 to go to 1. Okay, so that's good. We can kind of say tail.next is going to be equal to the head. And then I need to take maybe the next node, so this pointer here, and I need to remove this. If I do that, now 3 has really come to the front, 3 is pointing to 1, and 1 is pointing to 2. The issue that I'm having immediately, though, is that if I just have a reference to the tail, and I just have a reference to the head, I don't actually have access to this node. So how am I going to adjust the pointer behind to be equal to this next node? So that tells me that this approach probably isn't going to work, and I need to go with some other approach and find a better solution. Again, to some of you, what I just did may not have made sense. That's fine. It's me walking through and trying to understand how I can approach this and going through different avenues until I find the correct approach. I realize now that in order for me to do the rotation, I need to have access to the previous node, so there may be a different way that I need to go about doing this. So what we can say here is that rather than maybe taking the back nodes and moving them to the front, we could maybe take the front nodes and move them to the back. Now this solves our problem because if I have a front node and I move this to be behind 3, for example, well, I have access to the next node from the front node, and from 3 I have access to its next pointer. So I'm able to actually manipulate the 2 pointers I need to. Now what this is telling me is that rather than rotating the back elements, I'm going to rotate the front elements, but when I rotate the front elements, my solution is going to look a little bit different. So just look, right, when we have k equals 2, the official solution should be 3, 2, and 1. Okay, so we have 1, 2, 3 goes to 3, 2, 1. So if we were going to rotate the back elements to the front, then yes, k is equal to 2 because we need to do 2 rotations. But if we instead decide that we're going to take the front element and we're just going to move the front elements to the back, the required amount, actually k can just be equal to 1 because I just need to take one front element and move it to the back. I know it seems a bit weird. Let me walk you through another example. So I have an example on my screen and we'll start going through it. Now we started with k equals 1, but we actually convert that to k equals 3 because we know we're actually going to shift elements from the front to the back. So let's look at how we do a rotation one time. Now, in order to rotate 1 to the back, we simply take whatever the tail is and we point its next node to 1. So now we have what's known as a circular linked list where the tail node is pointed to the head node. Now, if we're only rotating one time, we could just remove this pointer and now we have a rotated list, and we would have 2, 3, 4, and then 1. However, that's not actually what we want. We need to do this 3 times. So really, we want to have 4, 1, 2, 3. So how do we know how to do that? Well, once I do this and I go 4 equal to 1, the next step would be just to repeat this process, but now we need to adjust our head and our tail nodes. So really, we're saying, okay, tail.next is equal to the head. That's the first thing we do when we want to rotate something. But now that we've done that, our head and our tail nodes have kind of changed, right? Now our new tail node is actually equal to 1, and our new head node is actually equal to 2, right? This would be the head. Now we're going to leave this pointer because we actually don't need to remove it, but we know that this now is the new head, and this now is the new tail. So now we can just really repeat this process, and we can keep doing this 3 times. Okay, so if we repeat the process, we say the tail dot next is equal to the head. Well, we already have that connection. Okay, so that's made. And then we just need to update the head and the tail. Okay, so let's go ahead and do that. So we can say now the new tail would be 2 and the new head would be 3. We can do the same thing again. Okay, so this now is our tail, this is our head. So we're going to say the tail.next is equal to the head. Okay, so again, that's already done. We don't really need to do that. And then we can adjust the head and the tail. Okay, so as we adjust the head and the tail, we now have the head is equal to 4 and the tail is equal to 3. Okay, now we're done the rotation because we've done this 3 times, right? Head is 4, which is what we want. Tail is 3, which is what we want. All we need to do now is we need to remove this link between the head and the tail. So if I can remove this link, now we have 4, 1, 2, 3. So the reason I just showed you that is that actually all we need to do to solve this problem, and it seems stupidly easy, is we just need to take whatever the tail node is, we need to connect that to the head node, and then we just need to go and find whatever the kth node is in our linked list and just disconnect its next pointer. That's actually the entire thing we need to do. So again, we begin, we take whatever the current tail is, we connect this next to the head, all these links will remain, and then we just go and find whatever the kth node is and just disconnect this next pointer and point it to null. So when k is 3, third node gets disconnected. When k is 2, second node gets disconnected. When k is 1, first node gets disconnected. That's all we need. That solves our problem. Okay, so in my horrible handwriting, I just wrote this out. We find the length, we simplify the k value, we perform the rotation. The rotation involves taking the tail.next, simply pointing that to the head value, and then we disconnect the kth node, and we're done. That's actually all we need to do. There's a few other small steps in between. For example, to find the length, we need to know how to iterate through a linked list. We're going to assume we know how to do that. To simplify k, there's a little bit of math. Again, we can write that in the code. To do the rotation, we need to find the tail node and find the head node. Pretty easy to do. We should be able to do that without having to write out a complicated algorithm. And then disconnecting the kth node, well, that just involves going through again and finding the kth node. So we're just iterating through the linked list. 1, 2, 3, 4. Oh, 4. Okay, disconnect. That's it. That's all we need to do. So now what I want to do is go over to the computer and show you how I would code this out. And again, as I code it out, I'll explain how I'm kind of coming up with that solution step by step. But really, this is the easy part now because we know what to do. We've written it out, we've diagrammed it, we've visualized it, we have a good in-depth understanding of not only the problem, but the solution we're going to implement. And now we just need to go to the code and write some kind of translation of this algorithm. So I'm back on the computer now, and we're going to start coding this out. Now, step 1 was to find the length, so let's find the length of this linked list. Now, to find the length, we can do the following. We can say length is equal to 0. We can then define a current node, which will be equal to the head, and we're going to say while the current.next is not none, then what we're going to do is say length plus plus, or plus equals 1, because I'm writing this in Python 3, and then we're going to say the current is equal to the current.next. I'm not really going to explain this. This is a very simple traversal of a linked list, which most of you should know if you're going into these type of coding interviews. Now, right away when I look at this, I realize there's a potential for an error in my code. The error is right here. Current, as we see, could potentially be none. it may not be one of the list nodes defined here. So before I can do this, I just need to make sure that the head node is not none. So I'm going to say if head is none, then I'll just return that head, because if there's no nodes in the linked list, it doesn't matter what k is, there's no rotation that we can perform. Okay, so now we should have the length equals 0, current equals head, well the current.next is not none, length plus equals 1, current equals current.next. Now what this actually does for us is at the end of this iteration, we have access to the tail node. The reason for that is when current.next is equal to none, that means that we have the tail because there's no more pointers, there's no more nodes in the list. So not only has this found the length, but it's also actually located the tail node for us, which is important because we need that for the next step. So once we find the length, the next step is to simplify the k value. So we're going to say our true k is equal to, and we're going to perform our simplification. Now the first simplification is to take k and to modulus this by the length of our linked list. However, remember that actually what we want to do is we want to kind of flip k around, and we want to do that by taking the length and subtracting that from k. So if we have a length of 5 and k is equal to 1, then we actually want to take the 4 elements from the front and move that to the back, as opposed to taking the 1 element from the back and moving it to the front. Again, it's effectively the same thing, but the way that we are going to solve this problem is important. So what we're going to do is we're going to put these in parentheses, and we're going to take the length, and we're going to subtract that from k mod length. That's going to give us the true k value, or the number of rotations that we're going from the front to the back because we've flipped the order. Now that we have the true k value, it's time to perform the rotation. So remember that the first step is to simply take the tail node and connect it to the head node. However, before I do that, I'm kind of realizing that if we have a node or we have a linked list where we have length 1, this could potentially be problematic because we could be connecting the head node to itself and creating this kind of circular infinite list, which we obviously don't want. So what I'm going to do is just do a quick edge case check here, something you should always be considering when you're solving these problems. And I'm going to say, hey, if the length is 1, it doesn't matter what k is. Again, we don't need to do any rotation. So let's just return whatever the head is of this linked list. So I'm going to say if length is equal to 1, then just return the head, just to make sure I'm not going to run into an issue here with a potential edge case of length 1. So I've kind of handled the edge case length 0, length 1. These are typically the ones you want to consider where you have nothing or you just have 1 element. So now that's handled. Now we can go and do the real rotations. So remember, we're connecting the tail to the head. So we're just going to say the tail.next is going to be equal to the head. But actually, that reminds me, we don't actually have the tail stored in a variable. So what I'm going to do is, instead, I'm going to say current, because this really is the head node, dot next is equal to the head, which was passed in. Okay, now we're just going to go and iterate through the linked list, starting at the head, and we're just going to remove the nth element's next pointer. Okay, so to do that, we're just going to say for, and we can say, actually, we're going to use a while loop. We're going to say current is equal to the head. We're going to say while, and we need some kind of count here. So maybe we're going to go with the for loop. We're going to say for I in range, and this is going to be, let's go with the true underscore k. And we're going to say current is equal to current dot next. Okay, so now what's going to happen is we're going to go and we're going to find that kth element, and then we're just going to remove that pointer. So I'm just going to say current.next is equal to none. So I remove that kind of circular aspect. I'm just getting rid of that 1 pointer that we don't need. So before I run this code, or before I would like submit this to my interviewer, I just walk through it and make sure I don't have any mistakes. Totally fine if you do have a few mistakes, by the way, and that's normal, especially if you're coding this out on a whiteboard. But you do want to just do kind of a quick check, just see if this makes sense. So if the head is none, okay, so if that's none, we're returning the head. Makes sense. Define the length, define current. Okay, we're going to say while current is not none, length plus equals 1, current equals current.next. Okay, iterating through the linked list. If the length is 1, return the head. Makes sense. True k value is equal to length minus k mod length. Okay, current.next equals head, so we're connecting that tail node, which we have, to the head. Okay, I think that makes sense. Current is equal to the head because we're now going to iterate through again. For I in range true k because we need to find the kth element. Good. Current equals current.next, so just iterating, and then current.next equals none. And then lastly, return actually the new head node. So this is the one thing that we're going to need to kind of have here is we need to know what the new head node is, which I kind of missed. So let's kind of go back in here and figure out how we would get that. So if we're saying here that current.next is equal to none, we're trying to disconnect the tail from the head, which means current.next is the head. So what we can do is say head is equal to current.next before we disconnect it. And then when we disconnect it, we still have access to the head, and then we should be good. So let's go for a sanity check here, and let's run this and just see where is the run button. Okay, run up here. Okay, so I just ran this code here, and I realized that we have a small mistake that we need to fix. So the first mistake here is with the length. It says 0 when actually we need to start the length at 1. The reason for this is that we're already accounting for the head in the fact that we say while current.next is not none, because we're assuming that we have at least one node, so we should start with the length equal to 1. Now we also have a mistake here in this for loop where I say for I in range true k. I need to actually subtract 1 from true k, and the reason for that is we've actually handled one of the rotations already by saying current.next is equal to the head. So when I do this, I'm rotating 1 too many times because I've already done one of the rotations with this manual line that we've written. So that's kind of the change that we need to do here. That should hopefully fix this for us now. There's maybe a more elegant way to write this solution. Keep in mind, I'm doing this live in front of you. I haven't seen this problem before, so this is what happens, right, when you're solving coding problems. Anyways, let's run this now, and hopefully this will work. And there you go. Now we have case 1 and case 2 accepted. Now that doesn't mean that this solution is perfect yet. What we can do now is we can submit this, and let's see what our results are and if this actually passes all of the LeetCode test cases. Okay, so there we go. We actually submitted this. It was accepted. It passed all of the different test cases, and you can see that our runtime beat 76% of people. I don't know if that's good or not. We probably could have done better and improved the space and time complexity here just a little bit, but overall I think this is a decent solution and hopefully kind of fulfilled the purpose of this video. So there you go, guys. I'm going to wrap up the video here. I hope you enjoyed and found this helpful. If you did, make sure you leave a like, subscribe to the channel, and I will see you in the next one.